Amirul is coming in. Okay, so I still, okay, now I can write. So the definition of a polymer is, number one, a long chain molecule. So everybody, as I'm writing, you just listen, no need to write anything. I'll send in the group later. A polymer is a long chain molecule that is made up of a combination of many repeating basic unit. Whatever I'm circling here, that's the thing you must remember. Okay, number one, long chain molecule. Number two, they are made out of many basic repeating unit. So you have many Chia Sungkiat. Okay, so all this was Chia Sungkiat. Okay, Chia Sungkiat. So many Chia Sungkiats here. When I undergo polymerization, I will get a long chain molecule. First keyword, a long chain molecule that is made out of many Chia Sungkiats. Okay, my basic repeating unit here is Chia Sungkiat. Today he's very popular. Poly means many. Okay, I was asking Fibi just now, polygamy you all know or not? Many wives, right? Okay, so this is polymer. Okay, many basic, repeating basic unit. Okay, so keywords, two keywords that I want you all to remember. What's my first keyword? You can type. I don't mind if you want to type. You can say it out loud. What's my first? Very good. It must be a long chain molecule. Very good. And my second one must be, it must be many repeating basic unit. Okay, well done. Kura, do you have the name list with you, Kura? In school, at home right now with you? Is Kura answering me? Okay, never mind. Okay. Teacher, move on. Okay, hang on, sorry. Oh, I'm stuck. Okay, so two things that you need to know. I'm going to go faster. I've got natural polymers. Natural polymers are things that you can find from your surroundings. Synthetic polymers, I make it in the labs. I make it in the factory. So natural and synthetic polymer. Okay, so example of natural polymers that you must know, you learn in bio as well. Starch. Okay, starch is a natural polymer originates from glucose. Okay, protein, okay, which is also your source of meat, is also coming from amino acid. Your amino acid is a type of monomer. So your glucose here is a monomer, your amino acid here is a monomer. So this is your natural polymer. Your synthetic polymer are examples like nylon, okay? You used to make ropes, threads, okay, clothes. That will be your synthetic polymer. So two types of things I just taught you, natural and synthetic polymer. Okay, four things that are important here. You need to know these four natural polymers. What are they? Starch. What's my monomer for starch? Glucose. Cellulose, my monomer is also glucose. Protein is amino acid. And if natural rubber, I'll teach you later. My monomer is isoprene. If you're writing notes, I want all of you to add on this one. Another name for isoprene is 2-methyl-buta-1,3-diene. Okay, that's why teacher has to teach you carbon compound soon. Because when you come to questions like this, some of you do not know how to draw them out or how to answer them. Okay, so then teacher has synthetic, okay, which is man-made. Okay, it's polystyrene, where you do your packaging, polypropylene. Okay, we use it for toys. PVC will be the pipes that you have. If you got any questions that you want to ask teacher, you can always put it in the chat group. Okay, now 3 types of polymers. If you can see teachers going fast. If I go fast in something, it's not so important. If I stay a long time there, it's important. Okay, this one is very important. Okay, I've got 3 types of polymers. Okay, what are they? Number 1, thermoplastic. I want everyone to imagine a plastic bag in front of you. A plastic bag is forever moving. Okay, and a plastic bag never stays in place. Okay, so the characteristic of a thermoplastic is I can repeatedly remold it upon heating. It doesn't stay in one place. It doesn't stay in one shape only. And I can recycle it. And we all know that plastic bags can be recycled. So I'm teaching you keywords here. Plastic. I've got Azimi coming in. I've got, I don't know who is this, Tanushri, Tiruguna, somebody. Okay, check whose family is that. Right? And thermoplastics, when teacher heats them up, okay, they will melt and solidify when they are cooled. So they can change from one shape to another shape. That's thermoplastic. Okay? And that's very, very interesting. Shavita, okay. All right, thanks. All right, that's thermoplastic. Okay, now then teacher go to thermoset. How many of you are very set in your ways? Okay, you're very set in your ways. You don't want to change. When you are thermoset, you cannot be remolded upon heating. So I've taught you thermoplastic. Thermoplastic, I can remold you. Okay, thermoset, I cannot remold you after heating you. When you're set already, can't change. Okay, and whenever you're heated up or burnt, you're completely disintegrated. I cannot recycle you anymore. Okay, so because thermoset, you're in one shape. Example will be a melamine and a bakelite. Go back to thermoplastic. Example will be polyethylene, PVC, and nylon. If I can have someone in class, I don't know, whoever in 5A, if you know, let Karishka not do this. If you already can look at the list and you know your friend is not in the list, I want you to type out their names, put in a list if you can. Kura, if you can help teacher, Kura. Okay, very quickly, doesn't have, just put whoever, and then if your friends can add on. I know Danish, I don't see Danish, I don't see Tashan here. So this is the two that I can offhand. Okay. All right, so I've got 10 more people, or 3 told teacher, 7 is not here. So I want to know who they are. Okay, now elastomer, polymers. Yeah, Sashina, Danish told teacher. Okay, the rest didn't, so I don't know where they are. So you better please go and get your friends, because if not, your friends were going to get from teacher, and when they get from teacher, they are in trouble. Okay, elastomer, I want you to imagine your grandma's house. Okay, and have you all seen your grandma having an old telephone, the one that can stretch? Maybe your own house has it. Anyone's house has it? No one.
The wire, is it?
Yes, the wire that is coiled. Yes.
Yeah, got it.
Got right? Okay, can you imagine now teacher take that wire and I pull it to the other side of the room. And then I did this to my brother when he was younger. And then from the other side, I will let it go. What will happen to my brother?
He would die, teacher.
He didn't die, thankfully. Okay, Kimmy just came in. He didn't die. All right, he is very much alive, getting married very soon. Okay, but he was in pain. All right, so elastomer polymers are something that I can stretch. Remember Puan Shina pulling, or you are pulling? Don't go and try in your grandmother's house if they have it. Okay, go and stretch, and then when you let it go, it will go back to its original shape. Okay, so that's elastomer polymers. Okay, example will be polyurethane and styrene butadiene rubber. Later, I'm going to go through it. So certain things I won't repeat here. So teacher spent a lot of time here. I want you to tell me the 3 types of polymer that I've taught you. Number 1.
Thermoplastic,
Very good. Thermoplastic example.
PVC or nylon.
Can PVC, nylon, accepted. Thank you, Rich. Very good. Number 2, another person. What is another one that I've taught? You can put in the chat. Teacher's happy if you do.
Thermoset, teacher.
Thermoset, very good. Example, Danish Vigneswaran is coming in. Okay, thermoset. Example of thermoset.
Bakelite and melamine.
Bakelite and melamine. Hopefully your textbook is not in front of you. Everybody looking and giving me the answer. I'll shoot you. Okay.
Food in front of me.
The food. Okay. What's my last one? The one that I did to my brother. What did I pull? What is it called? Elastomer. Very good. Yeah. Elastomer. Not elastic, elastomer. And it can be stretched and go back to its position. Tell me one of the settings or characteristics of a thermoplastic.
Can be remolded easily.
Can be remolded. Okay, very good, Jawi. Okay, Jawi cannot answer D. That one is elastomer, can go back to its original state, Sharifah. Good, you gave one for elastomer. Now the second one, how about thermoset? What is one of the thing for thermoset? Cannot be remolded upon heating. So I want you all to tell me later on. Y'all tell me number 1, number 2, or number 3. Put in the chat group. Which one are you? Are you an elastomer? Okay, something happened to you, you can go back to your original position. Or are you number 2, so set in your ways? Or are you number 1, you are flexible? Okay, put in the chat group. Everybody's going to watch now. Okay, are you 1, 2, or 3? No one dared make the first move. Okay, teacher will give. Rishi says 2. 1, thermoplastic. Okay, thermoset. All right, fair enough. You've got your own justifications for that. Okay, very good. Yeah, good job. Well done, well done. Okay, so I've started. Okay, you can continue giving your things here. Okay, I'm gonna now go to addition polymerization. When you see the word addition, you must have carbon-carbon double bond. Okay, carbon-carbon double bond. Okay, so you don't know what's carbon-carbon double bond because I didn't teach you chapter 2. That's why I have to teach you concurrently. Okay, so what is happening is, watch what teacher is doing here. I've got carbon-carbon double bond, and it will add with another carbon-carbon double bond. Remember I said chia. So this is one chia plus another chia monomer plus another chia monomer. So many chia monomers here. I'm going to add them together. So only when you see a double bond, you will know, it's going to undergo addition polymerization. Why? Okay, let me show you why, because I'm going to do it up here. What happens is, just going to have, this is called an ethene group, yeah? Ethene group, it's going to undergo polymerization. I'm going to break the double bond here, and I am going to form another bond. Okay, remember I told you n number of chias? Okay, so then teacher is going to undergo polymerization. And when I undergo polymerization, I'm going to rewrite everything. Now, in the middle here, my double bond is no more a double bond, it's a single bond. And I'm going to write my H on top. It's just very easy. I like chemistry a lot because it's just always copying back things. Okay? And then in carbon, one carbon must have 4 wives. Always remember that. One carbon must always have 4 wives. Now, this carbon got 1 wife, 2 wives, 3 wives. Cannot be. Now, this carbon on my right, 1 wife, 2 wives, 3 wives. Cannot be. Each carbon must have 4 wives. So remember, I broke a bond and it went out here. So I'm going to draw a line here, and another bond went out here. I'm going to draw a line here. Okay, now can you see right now, each carbon got 4 wives, 1 wife, 2 wives, 3 wives, 4 wives. I'm going to close here. Same thing, I've got 1 wife, 2 wives, 3 wives, 4 wives. I'm going to close here, and I'm going to put N. And this is what we call polymerization. Okay, if y'all can write it in your notebook or whatever you have in front of you, it'll be really, really good. So I'm going to give you another example for you to try, and I want you to tell me what answer do you get. Okay, all of you try together this one with teacher. Teacher has the C double bond C. Now I've got something else here. I've got a CH3 here. I've got a H. I've got a H. I've got a H. If it undergoes polymerization, why? What is it going to get? What am I going to produce? Okay, teacher is going to put the word polymerization here. Okay, and this is n amount of monomers. What is my product going to be? Who would like to try? You can actually say it out loud, so teacher can draw it out for you. What do I have to first do?
Copy back everything but break the double bond.
Very good. I copy back everything. Okay, and then I break the double bond, correct? So CH3 here, H here, H here, H here. Now, if you notice, I don't have enough wives. No, the carbon don't have enough wives. The carbon, all right? So what do I need to do?
Put 2 bonds on the side. 2 more wives.
And you add 2 more wives. Where do I add 2 more wives? Anyone else? Thank you, Rishi, for trying. Yeah, but the rest also can try. PT Rishi have to answer all my question. Anyone else who wants to try? Okay, if not Rishi, let's not waste time. Rishi, give me the answer.
Add 2 wives and then close the bonds and right
then?
hand.
Very good. That's it. That's all you need to know. Okay, so when you see a double bond, what polymerization is it? You can put it in the chat. You can answer teacher in the chat. You see a double bond, what polymerization is it?
Addition.
Very good. Thank you, Sharifa. It is addition. Well done. Okay. Student is coming in. Kura, could you help teacher? Or even Shiva, whoever. Just add on the ones who are not here. Okay, just add on the ones who are not here. Add in then Danish, put that late. Add in student, put that late. Okay, all right. Correct, but we're not going there right now, so we'll wait to teach you on that one. Okay, so these are examples of your any polymer that is undergoing addition polymerization. You see each of them has a double bond. Double bond, double bond, double bond, double bond. Okay, and if you notice what I taught you just now, I break the bonds, I add more Y's to them, and then I have an N there. Same thing. Okay, but each of them have a characteristic and they have a use. So teacher wants you to memorize one. Okay, 18, I use it for plastic bag. Just memorize one will do. 18, plastic bag or plastic bottles, enough. Propene, toys. Okay, polyvinyl chloride, you and I know, water pipes. Okay, styrene, we use it for food packaging. Okay, so beside Rishi and Sharifa, one person telling me what's the use of 18?
Plastic
Or
bag.
plastic bag.
Very good. Plastic bags. I heard so many answers. Okay, very good. Next one. What's the use of propene, polypropene?
Toys.
Toys. Very good. Yes. And what's the use of PVC?
Pipes.
Pipes. Very good. And what's the last one? Polystyrene?
Food packaging.
Food packaging. Very simple. Very good. Okay, I'm now almost going to finish my 4.1 already. Okay, so this is what we just did. Okay, chia plus chia plus chia plus chia plus chia plus chia. I get polychia. But don't stress out. What I taught you just now, this is enough. You break the bonds, you add 2 Y's, you're happy already. Okay, this is what I want. Don't forget your N. This alone is enough. Okay, now look, this is called addition polymerization, and it only happens when I have double bond. I'm going to go to my second one. It's called condensation polymerization. Condensation polymerization is when I 2 monomers react, but my side product that comes out is a water or a hydrogen chloride molecule. Okay, don't be stressed with what you see right now. Don't be stressed. Okay, because when I do questions with you sometime later on, then you will be able to understand better. Just look at what I'm going to show you. Do you see any double bond between the carbon and carbon here? Do you see any carbon-carbon double bond?
No, teacher.
No. Okay, so when you don't see any carbon-carbon double bond, what happens is you will straight away know it's a condensation polymerization. And what happens is I must take out water or I must take out HCl. In front of me, it's so obvious, I am going to take out water. Okay, one hydrogen must come from one monomer and another OH must come from another monomer. So 2 different monomers. Okay, and then they are combining together. So here, teacher take out water. Now remember, if I'm taking out water like this, here also teacher will cut off the OH. And here, teacher will cut off the H. Okay, So if teacher's going to combine all of them together, again, chemistry, I just rewrite everything back again. Because I cut this off already, I start with the O. My O is here. My C2H4 is here. My C2H4 is here. My O is here. My O is here. Where I cut, I connect again. So this is my C and O. C and O. My C and O connected to a benzene ring. This is a benzene ring. Connected to a CO. Connected to a CO because I cut here. So I got the line here and the line here, close bracket, it is an N. My side product is water. Now, it doesn't matter, teacher, I don't get what you say, it's fine. What I wanted to point out to you was that I've got one addition polymerization, another one is called condensation polymerization. And you will know it's condensation polymerization because in between here, you must take out water. You will surely know, okay? And your product is always a tyrolene, okay? And you will get an ester here. A lot of things you don't know what I'm saying because I haven't taught you carbon compound. So it doesn't matter, just hang on. Okay, another compound that is formed through condensation is when I take out HCl. Just now I told you when I take out water, now I'm going to take out HCl. Okay, teacher, take out HCl here. Okay, I'm going to take out the H here, take out the Cl here because I'm forming another HCl. If you notice, I'm writing back the same thing all the way here. Teacher, take out the HCl, I combine to the CO. Combine to the CO and I copy back everything here. All these are back here. And that's it. Okay, this is your condensation polymerization. If you say, teacher, I don't know how to draw, it's okay. For now, you don't need to draw. For now, you need to differentiate condensation polymerization and addition polymerization. That's it. And remember, they are always my side products. Okay, I've taught you two polymerization. What are they?
Addition and condensation.
Very good. Addition, condensation. Okay. Now, Natal teacher, how do I know when it'll be addition?
It got double bond.
Okay, got a double bond. Okay, cannot answer anymore already. The rest of you, how do I know it's condensation?
No double bond.
Thank you, Jawe. You don't have a double bond. Okay, and I've got two different monomers. That's now the same. Cha. Okay, condensation is not cha anymore already. There are two different things that I'm adding together. Okay, so actually I would love to do a synthesis of nylon with y'all in the lab. Unfortunately, I've searched for so many schools. Okay, they do not have for me diol dichloride. Okay, so I'm still searching and I'm hoping that we can create our own thread. Okay, this is actually a thread. Okay, it's very nice to do. This chapter got a lot of nice experiments. Okay, let's try and pray that I can still find more. Okay, where do I use polymer in my daily life? You know, I just told you, medical, even our lab apparatus, plastic bags, nylon, your threads, okay, acrylic polymer for waterproof roof. Okay, so these are some examples of polymers. Polymers good. Adib is coming in. Karishka add on late, yeah. Is polymers good for us? No, because plastic is not good for environment. But bio talks about this. I'm sure BM also talks about this. So teacher won't waste time telling you all about all the effects. You all can go and read on your own. Okay, so we need to recycle. We need to use biodegradable plastic cups. Okay, all these you all can read on your own. Teacher's done with 4.1. Do you all understand roughly 4.1? I don't expect you to understand 100%. I expect you to only to understand at least 60% of what I teach. And do you understand 60% of what I teach?
Yes.
Okay, 5A. I would like you all to jot down the name of your friends that are not here. Okay, 5B, I'm going to check shortly. So I'm going to give you a 1-minute break. Okay. And I am hoping that I can get the rest of y'all to add on the names. 5A, Kura, if you can help teacher. So I've got 6 more names. I have got, wait, yeah. So if I say come to class and none of y'all inform teacher, then a teacher won't accept that. Yeah, I know someone who is sick who is still here. Okay, so I have Sash, I have Danish. So I've got 4 more kids who are missing. Who are the 4 more kids missing? Can list everyone in 5B, is there?
Harriet and Mervin is not here.
Sharvin? Elijah?
Oh, yeah, also not here.
Okay, put it down in the group. Okay, so if you, I know the other one will be Tashan. I know Tashan's not here. Add on Tashan's name and then 1 more. Okay, now, and 1 more. I can't remember who's at 1 more. Who can help? Candice, for 5B, I want you to write down the 3 boys. And then Haris. Okay, Mel did mention to teacher. Okay, so it's okay. All right, so I am going to wait for a minute because I want to wait for all of them to figure out who's coming and who's not. Who's the 1 more person? Can we not figure out who that 1 more person is?
Ashwin isn't here.
Ashwin, okay. I still got 1 more, right? We've got 35 in class, right? So I've got 29, 30, 31. 1, Ashwin, 32, 33, 34. 1 more? Who's that 1 kid who's missing? Raja. Am I right? Is Raja in? Okay. Raja, so, all right. Azimi, call 1 if you can. Jawed, call Ashwin. But he didn't tell teacher. So I will not accept that. Okay, if you tell me, I can accept. Okay. Tashan, I want Ashraf to call. And Raja, teacher would like Loga, you call. Okay.
Teacher, I will leave the call a while so I can call Ashwin.
Why? You can use your brother's phone?
Oh, yeah, right. Okay, so I just
Twins. All right. Okay. Done. Okay, we settled the mystery of the missing guy. Okay. Okay, let's move on. Natural rubber. Okay, so how many of you have seen latex before? How many of you have tapped a tree before? I had one student tell me last time that the grandfather owns a plantation. Ah, very nice. Okay, what color is the latex? Okay, obviously white in color. All of y'all should know that. It's a white fluid, okay, obtained from the rubber tree when it's being tapped. Okay, very good. Okay, want to know why are you teaching us natural rubber? Why are you teaching us latex? Because if you didn't know, okay, natural polymer is found in latex. And my natural polymer that is found in latex is actually natural rubber. And remember just now I told you to write down 2-methyl-buta-1,3-diene. Okay, that 2-methyl-buta-1,3-diene, that is my natural rubber. Okay, and when it undergoes polymerization, it will become a polyisoprene. Okay, which teacher will teach you later on. Tashan is coming in. He doesn't know there's chemistry class. How? Didn't I say got chemistry class?
teacher, Ashwin not even pick up my phone.
Okay, never mind. It's okay. Thank you for trying, Ashraf. Thank you for trying. Jawi, thank you. All right. Okay, doesn't matter. Okay, let's see. Okay, so we move on. Now, in my rubber particle, okay, this is called a rubber particle. A rubber particle has rubber polymer inside. I don't want you all to mistake. the rubber polymer is inside. This is called a rubber polymer. The whole thing outside here is called the rubber particle. This rubber particle has negative charges. All around the particle, they have negative charges, causing them to repel one another so that they won't coagulate. Okay, this circle that I'm circling right now is called a protein membrane. This protein membrane is negatively charged. Okay, so when you go and tap rubber, why doesn't the rubber combine together and coagulate? Coagulate means they are clumped together, or they are combined together. Why does that not happen? Think about it. Why do you think that when you're tapping the rubber, it's liquid and it doesn't solidify at all?
Because it has a protective membrane around it.
Wrong. You could try. The answer is right in front of you, staring right in front of you.
Negatively
Is
charged.
it- Yeah.
Very good. It is negatively charged. Because it is negatively charged, it will repel each another. So I'm going to draw it here for you. I've got negative charge here, one protein membrane here, another one, another protein membrane here. So they can't even come near each other. When they come near each other, they will totally repel each other. So the particles cannot collide, the polymers inside it cannot collide. That's why it's forever going to be in a liquid form. Okay, so this is something that you need to know. I have a protein membrane and my protein membrane is negatively charged. And they are negatively charged and it doesn't allow them to coagulate. Now, latex is a colloid. You learn in Form 2 that, okay, what is a colloid? How can I compare a colloid from a solution? Yeah, Form 2 topic. A solution, I can see clearly. It's transparent. I can see from one side to the other. A colloid, I can't. Okay, there are solids in it. Okay, that's the difference. It's called a colloid. Your jelly, okay, jelly is a kind of colloid as well. Okay, so take note. Okay, colloids is something that is you need to know. Okay, now natural rubber, are they good or are they bad? You need to try. Okay, Danish say good. Rishi, you said something, but I didn't hear you.
I say good.
Okay, they're actually not good. They're the bad boys. Okay, they're not so good. Okay, you look at their characteristics. Okay, soft. Okay, they're very soft. You don't want something that is soft. Okay, elastic. Okay, elastic, okay, good, not a problem here. It's got low heat resistance. That means when at very high temperature, it becomes very soft and sticky. Okay, electrical insulator, they cannot conduct electricity. Memang good usulah. Okay, I can easily oxidize it, which is not good. You do not want something that you can easily oxidize. Okay, reactive to chemicals. Who wants something that is reactive to chemicals? You don't want that. Okay, imagine you're tired, touch an acid, gone. You wouldn't want that. Okay, your shoes, touch acid, gone. So natural rubber is actually not so good. Okay, it's waterproof, but of course, water impermeable. Okay, so actually natural rubber, the characteristics is not so good. So later when I teach you vulcanized rubber, okay, when I teach you vulcanized rubber, we will see why. Okay, so where do I use natural rubber? The things that I'm going fast, that means it's not important for exam. Okay, tires, boots, your rubber bands, soles of your shoe, gloves. Okay, so all these are the uses of natural rubber, which you can actually go and read by yourself. Okay, now teacher wants to teach you this. This is the mechanism. Okay, how can I make coagulation happen? And how can I prevent coagulation from happening, which we will do an experiment next week. So I'm going to take the latex we read. I'm going to label 3 beakers, beaker A, beaker B, beaker C. And then I take latex and I pour it into each beaker. Beaker A, beaker B, beaker C. Teacher draw here, A, B, C. Okay? A, teacher going to put acid. B, teacher going to put alkaline. What's the alkaline that I'm using here?
Ammonia.
Very good. I'm using ammonia. What's the acid that I'm using here?
Ethanoic acid.
Ethanoic acid. Okay, and the last one, I am just going to leave it. I call it as my control. Okay, so teacher's going to leave it. Okay, now let's see what's going to happen. Watch. When teacher take latex and I put with acid, coagulation happens. That means to say, the particles will, the rubber particles or rubber polymers will coagulate, combine, and become a solid. But when teacher put an ammonia solution, nothing happens at all. It does not coagulate at all. What is the theory behind it? There's a theory behind it. Okay, so here the theory is very important, and this is what I am going to explain to you, and you better listen carefully. Number one, which all of you should know, and I've established already, I said, the negatively charged protein membrane causes the rubber particles to repel. So if you notice, this is my protein membrane. They have my rubber polymer inside, and it is all negatively charged. Rubber polymer inside, negatively charged outside. All of you should understand picture number one. When I go to picture number two, I have got hydrogen ions. Now, my hydrogen ions can come from two places, which we will go through shortly. Number one, my hydrogen ion can come from my ethanoic acid, which we just did. Okay, the hydrogen ion comes from here. Or if I leave it in air, there's bacteria in air. And when I've got bacteria in air, bacteria carries what acid? What acid does it have? Bio kids?
Lactic acid.
Correct. I've got lactic acid. Now, both this acid, I've got hydrogen ions. Okay. Now, what happens is I will go, the hydrogen ions will come in. Okay. As you can see, the green color one are hydrogen ions. The hydrogen ions will now come and neutralize. I'm only doing for one protein membrane. Teacher got no time to do for all. Okay. The hydrogen ions will come and neutralize completely this whole negatively charged protein membrane. Okay, so the key word I want to see is the word neutralize. Do not come and tell me react. I don't want. Okay, so hydrogen ions from the acid will neutralize the negatively charged protein membrane. So I'm going to draw it again just here for you so you can see it clearly. I've got hydrogen ions, hydrogen ions, hydrogen ions, hydrogen ions, hydrogen ions. Cancel, cancel, neutralize, neutralize, neutralize. What happens? Do I have anything else left outside my protein membrane now? Do I have any charges or any hydrogen ions outside my protein membrane?
No.
Nothing, nothing whatsoever. Okay, then you look at my third slide. Okay, my rubber particles now will collide with one another and cause the protein membrane to break. So that means I've got nothing already here. Okay, nothing at all here. Okay, my rubber particles will collide with each another and then my protein membrane will break. Okay, when my protein membrane break, watch. All my rubber polymers can combine. The word is combine. Do not use coagulate yet. My rubber polymers will combine and then they will cause the latex to coagulate. Let's go through the 4 steps. What's step number 1? Cannot just be 2 persons answering, teacher. If you want to put it in the chat, it's fine. Okay, let me know you are here. Number 1. Teacher's not going to let you go. If you all don't answer me, you're going to stay here with me until tomorrow then. What's number 1? If I call name, lagi teruk for you. Cannot bank in on one person to always help you. Just try. What's the first picture? The first picture where you've got protein membranes, then you've got the negatively charged. So what can you say there?
They repel each other.
Very good, Banu. Good job also. Talija. Okay, negatively charged protein membrane cause the rubber particles to repel. Well done, both of you. If you can, do not refer to any textbook. Just try on your own. If your answer is wrong, so what? It's okay. You're learning just on the spot and you're recapping. That's really good. I'm really happy if you're able to do that. Okay, second picture. What comes in?
It neutralizes.
Very good. Okay, I've heard Mai, I heard Shiva. So maybe they can complete each another sentence. Hydrogen ions does what?
Neutralizes the negatively charged protein membrane.
Very good. Okay, good Shiva, good Mai also as well. The hydrogen ions neutralizes the negatively charged protein membrane. Well done. Third picture.
Rubber
The
particles collide.
membrane breaks.
Very good. Okay, I hear Wong, Sharifah, and Kama. Rubber particles collide with one another. Very good. Collide. Okay, well done. Okay, when they collide, then what happens? And they break. You must mention, I cannot just say collide. I collide only, then what happened? Must say break. Protein membrane breaks. Okay, and I want to tell you, if you don't put the word protein membrane and you have all the sentence, but you forget the word protein membrane, you lose your marks completely. Okay, very good. The last picture, I see. Wait. Okay, I see Amirul, I see Sharifah, I see Danish. Danish, who's above you, Danish? Can't seem to go up. Who wrote above Danish?
Carbon.
Kevin, okay. So, and Amirul, okay, very good. So the rubber particles, so rubber polymers, inside is polymer. The rubber polymers will combine with each another and then they will coagulate. Do you all understand that so far? Okay, so very good. I think all of you basically got the picture. Okay, now watch. Okay, Rishi ended it. Well done. Okay, so if you look at my coagulation process, it's exactly what you just said or exactly what teacher said. Okay, when I add a weak acid or I leave it in the air, coagulation will take place. Weak acid, teacher can put CH3COOH. Can I put a strong acid? I can, but then it will react with my latex so much, and I don't want that. I want just a simple reaction. So we don't usually use a strong acid. But when I leave in air also, I will have a lactic acid. And my lactic acid has hydrogen ions. So both ways, whatever I just taught you, works. Okay, my bacteria in air also will secrete lactic acid and allow it to coagulate. Okay, so yeah, this one is nothing. Now, how can I prevent coagulation from happening? So if you know acid allows it to coagulate, what doesn't allow it to coagulate?
Weak alkali.
Very good. It's a weak alkaline, which is your ammonia. Very good. So many of you gave me the correct answers. Well done. Okay. Sorry if I don't mention names because I'm just trying to rush for time. Yeah. Okay. So I'm using ammonia. It's weak and it makes sure it ensures that coagulation does not take place. Why? Because alkaline has hydroxide ions. Okay, teacher, where got ammonia? I don't see any OH there. So aqueous ammonia is actually NH4OH. How do you, teacher, how did you get that? So it's actually NH3 plus H2O. You're going to get NH4OH. If you work out the math and everything, okay, the numbers, you will notice that the numbers before and after tallies each another. So the alkaline solution here will neutralize the acid produced by the bacteria. So you might be thinking like, teacher, what happening here? I don't get it. So let me just explain. I have negatively charged protein membrane. I have my rubber polymers inside. Not I'm putting is the OH straight away. No, because I leave it in air still for a while, hydrogens will come about. Okay, the hydrogens will come about but before it can neutralize the negative ions, I already put in my alkaline solution, which is my OH minus. OH minus. OH minus. OH minus. OH minus. Minus. So it will neutralize the H and OH, 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 H and OH. I think I'm talking too much today. What is ester? Are you asking me a question, Rishi?
Yeah.
Okay, so this is an ester. But I know it doesn't mean anything to you until I teach you carbon compound. But you can see me later on after class and teacher will explain further. Okay, but I'll finish this first, yeah? So when all of these are neutralized, you tell teacher what is left now on my protein membrane. What do you still see there?
Negative charges.
Very good, Aiden. I still see my negative charge. And because I still see my negative charge, what's going to happen? Are they going to repel? Or are they going to, very good, they are going to repel each another, correct? Okay, so the protein membrane, it remains negatively charged. That's why it will repel and it will not coagulate. So I asked, it came out in trials before. If you were a rubber tapper and you want to go from one place to the other, justify the actions. Would you add acid or would you add alkaline? Okay, and during the exam, they accepted both answers. Some people say, I want to add acid, I want to make it solidify. Then when I reach that place, when I want to travel, the latex will not spill. Okay, some people say, no, I will leave it in its original condition, therefore I will add alkaline. So it depends on how you justify your answer. They accepted both answers. So you must know the knowledge of both. Okay. If I can do this experiment with you, I will try doing this experiment with you. Okay. Oh, no, not if. We will do this experiment. It's very fun. Okay. We are going to produce a product from latex. You can bring various things that you want to put in shape, and then we can make a product from latex. Okay, so now remember I told you natural rubber is a bad boy. Okay, so we want a good boy. All right. So how to make it a good boy? We vulcanize that rubber. Okay, we make it even better. Okay, and during vulcanization, it will form sulfur crosslinks. And this sulfur crosslinks makes vulcanized rubber even stronger. Okay, so if you remember my name, what's my full name? Wow, none of you remember.
Leslie.
No, actually, that's not my full name. It's somewhere here. It's I've always said it for salt, insoluble salt. Correct. Okay, Raphael, it is correct. You forgot, smack you. Okay, it's actually Sheena Sivakanithan, yeah? So you can see in chemistry, you can see a lot of Sheena SS in chemistry. It's just meant me to be in chemistry, to be a chemistry teacher. SS here. Sheena Sivakanithan, Sheena Sivakanithan, Sheena Sivakanithan, Sheena Sivakanithan. So you cannot forget sulfur crossing, okay? From a good boy, the bad boy to become a good boy, you must add Sheena Sivakanithan. Totally wrong concept, but just remember what I'm just saying, okay? So in order for vulcanization to happen, you must have a double bond. It only can happen where the double bond is. Don't worry, when teacher do question with you, I'll explain further. So when I break the double bond, then I have got lesser bonds, which means to say now it will form as a sulfur link from one carbon on top to the carbon at the bottom. From the one carbon on top to the carbon at the bottom. One carbon on top, one carbon at the bottom, one carbon on top, one carbon at the bottom. Okay, I'm going to draw me here. Who's the smallest kid in class? Girl lah, got girl or not? I don't think I can hit student. Okay, this is Kura. This is Puan Sheena. This is Kura. So I go towards Kura and I simply push her. She also jatuh. Okay? Sorry, Kura. All right. Now imagine there is this big guy here. Okay, who shall we name this big guy?
Raja.
Okay, Raja. All right, alamak. Okay, this is Raja. Now, I am trying to push Raja to push Kura. Do you think it will even happen? I'm trying to push. No, impossible. Raja will be the one pushing me back. Okay, so the SS here is actually the same concept, Raja. He's so strong, sulfur cross-links, that no matter what happens, it will not move. It is such, it makes my vulcanized rubber strong. So how do you know, teacher, how do I know something is a vulcanized rubber? Okay, when you see that you have sulfur in it, that's a vulcanized rubber. Okay, that is your vulcanized rubber. So I just read something that Shiva wrote. Okay, so again, I would like to try to do this, but I can't find disulfur dichloride. If I do, I will let you all know and we can try it on our own. Okay, this one not important. Okay, this one is not important. I'm going to go very fast. If let's say I do not want to do vulcanize, what are other ways? Okay, more than objective. Before you can use peroxide method, metal oxide irradiation method. Because I want vulcanize, I'm using sulfur. Okay, and all these other methods here, they are more environmental friendly. So read up on your own. I don't need to teach you on that one. Okay, then I go to the next one. I've got a vulcanized rubber. And I've got an unvulcanized rubber. I take both rubber and I put a weight on it. Okay, and I put a bulldog clip to hold it. And then I, like elastic, I told you, I pull both of it down. And then I let it go. Which one you think will go back to its original position and which one wouldn't? You tell me.
Vulcanize will go back. Original.
Very good. I heard even my answer as well. Vulcanized will go back. Okay, unvulcanized will not really go back. Okay, so look at the diagram that I have at the bottom here. It explains very well. Okay, so I use this example just now. This is all of y'all in school in the morning. Okay, all of y'all are okay lah. Before stretching, y'all are a bit flexible and all. Then in school, okay, y'all are so stretched. Okay, y'all are your minds, your body all used up. And then when y'all reach home, or during extra class or whatever, or even right now, this will be y'all. Am I right? Give me a thumbs up if my answer is, if I'm right. Definitely not. Okay, that's unvulcanized rubber. It does not, you see, you compare in the beginning, before stretching, and in the ending after stretching, it's not the same at all, completely different. But when I have vulcanized rubber, my sulfur crosslink here, before stretching, it's like that. During stretching, it is more stretched, it's more tensed up. But when after stretching, it does not completely lose itself. It loses a little bit, but it still maintains its position. So vulcanized rubber definitely is much better. Why? They like to ask, because strong sulfur crosslinks will prevent the rubber polymer from sliding. Okay, these crosslinks here will prevent my rubber polymer from sliding to its original position. Okay, I'm gonna move on. Okay, now good boy, bad boy. Okay, vulcanized rubber, as I said, is a good boy. Okay, it's more elastic. It's hard. High tensile strength. I can put a lot of strength on it and it's okay. Resistant towards high heat. Okay, and it's more resistant towards oxidation. Unvulcanized, bad boy. It's less elastic, soft. It's got low tensile strength. Less resistant to heat. Easier to be oxidized. Okay, so these are the difference between the vulcanized and unvulcanized rubber. Teacher has finished 4.2. Okay, I'm going to go to 4.3 and that's it. No more. So teacher has synthetic rubber. I take 30 seconds to drink some water. What's the meaning of synthetic?
Man-made.
Very good. It's man-made. Okay, it is naturally, is elastic naturally, or is an elastomer polymer. Remember, in the beginning I taught you elastomer polymer. What are some of the examples of elastomer polymer?
SBR.
Very good, SBR. One more.
Poly.
Urethane.
Yeah, polyurethane.
Polyurethane. Now you go and double check. It's okay. As I said, cannot memorize everything. It's fine. They're just completely okay with that. Okay, so most of my synthetic rubbers, I cannot find it naturally. Impossible. It's a byproduct of petroleum. Okay, and why must I have synthetic rubber? Why can't I just use natural rubber? Because natural rubber, we don't want to finish it. And natural rubber, it takes time. Okay, synthetic rubber, I can produce it straight away in the factory. It doesn't take time to make it. Natural rubber, I need to tap the tree. I need to bring it to the factory. I need to do process on it. Synthetic rubber, I can just make it. So that's why we have synthetic rubber. Synthetic rubber is very similar to vulcanized rubber. It's very good properties as well. Resistant to heat, to chemicals, oxidation, heat insulator. It's elastic, it's hard. Okay, so example, as I said just now, is neoprene, SBR, silicone rubber. Yeah, I'm just waiting for it to finish. Okay. Synthetic rubber, I used it. It was first invented in the 20th century to replace natural rubber. As I said, we do not want to we don't natural rubber to completely be finished, okay, or completely used up. That's why we came up with synthetic rubber. Okay, this one is very important. Came out before. So you need to at least know a few examples. So we've got neoprene. Okay, it's high heat resistant. It's resistant to oxidation. Flame resistant. Where do I use it? So your conveyor belts, anytime you see conveyor belts, remember synthetic rubber. Your petrol rubber hose, your gloves, okay, you're using neoprene. Okay, SBR, usually for your tires and your shoe soles. Abrasion resistance, okay? You want to avoid, make sure there's good friction. And obviously high heat resistance because you're traveling on the road. Okay, you're using your tire, there's a lot of heat also involved. Okay, so you want to make sure you use a good quality rubber. Okay, silicone rubber, I've got high temperature resistant. It's very inert, it doesn't react. Okay, so I can use it in cooking utensils. Why? Because it doesn't react with my food. Okay, medical implants. Okay, I use it in sealants. Sealants are things that I use to glue things together. Okay, thiocol, sorry, sealants, and also last one, nitrile rubber gloves. So these are some examples that you must know. I'm almost going to finish already. What's the use of rubber and the environment? Now you need to know that synthetic rubber takes a long time to decompose, very difficult to dispose it. So if you go to our taman in school, do you all see the tires there? Have you all seen the tires in the taman?
Yes.
All right, okay. And it's actually very good when you have tires that you don't want to use anymore. Please make sure that you recycle them or you reuse them, okay? So that we do not waste, okay? Or we do not cause pollution to the environment. That's it. My voice can't take it anymore, so. And that's it, class. I've finished chapter 4. Thank you, class. I will